Hello, welcome to 3.2, Rolle's Theorem and the Mean Value Theorem. So Rolle's Theorem, let f be continuous on the closed interval from a to b and differentiable on the open interval a to b. If f of a equals f of b, then there's at least one number in ab where f prime of c is 0. So what it's saying is if you have a curve like this one here, where f of a equals f of b, there must be some place in between where the derivative is 0. If it's continuous on the interval. So there must be a place where the derivative is 0. So find the two x-intercepts of f of x equals x squared minus 6x plus 8 and show that f prime of x equals 0 at some point between them. Okay, so we have f of x equals x squared minus 6x plus 8. So we do x squared minus 6x plus 8 equals 0. That's x minus 2 times x minus 4 equals 0. X minus 2 is 0, means x equals 2, and we see that here. X minus 4 equals 0, so x equals 4. And we see that there. So someplace between 2 and 4, we're going to have 0 as a slope. F prime of x is going to be 2x minus 6. So where's 2x minus 6 equal to 0? That's where 2x equals 6 over x equals 3. And 3 falls between 2 and 4. So f prime of 3 is 0, and 3 is in the interval from 2 to 4. That's Rolle's theorem. Kind of cool, huh? Okay, I'm going to go on to example 2 now. Determine whether Rolle's theorem can be applied to f of x equals x minus 1 times x minus 2 times x minus 3 on the closed interval from 1 to 3. If so, find all the values of c in the open interval from 1 to 3 such that f prime of c equals 0. So just to kind of get a visual on this, we have an intercept at 1, at 2, and at 3. So it's going up here, coming down there, and then going up again. Something like that. So it looks like we do have a turning point in each case, so we would have a 0 there and a 0 there. So it would apply. We know that f of 1 is going to be 1 minus 1 times 1 minus 2 times 1 minus 3, and that's going to be 0. F of 3 is going to be 3 minus 1, 3 minus 2, and then 3 minus 3. Of course, that part's 0, so it's 0. So Rolle's theorem can be applied. Okay, so f of x, by the way, if you multiply this all the way out, it's going to be x cubed minus 6x squared plus 11x minus 6. F prime of x is 3x squared minus 12x plus 11. So where's 3x squared minus 12x plus 11 equal to 0? If we use the quadratic formula, we have x equals negative of negative 12 plus or minus the square root of negative 12 squared minus 4 times 3 times 11. All over 2 times 3. That is 12 plus or minus the square root of 144 minus 132. All over 6. That's 12 plus or minus the square root of 12 over 6. 12 plus or minus 2 root 3 all over 6. And that can be reduced to become, let's do that, 2 plus or minus square root of 3 over 3. So if we do 2 plus the square root of 3 over 3, we're going to be at 2.58. If we do 2 minus the square root of 3 over 3, we're going to be at 1.48, 1.42. So C equals 2.58 and 1.42. Okay, so that was fun. Rolle's theorem is really cool. We can really use it here and find these places. Let's go on and talk about another one, the mean value theorem. I like the mean value theorem even more. And if you read these notes, as I hope you have, and read the book, if you read these notes, you'll see my enthusiasm here. The mean value theorem, if f is continuous on the closed interval from a to b and differentiable on the open interval from a to b, then there exists a number c in ab such that f prime of c, get this, is f of b minus f of a over b minus a. Now what does this look like? This looks like the equation for the slope. This is slope between 2 points. So if you have 2 points, a f of a, b f of b, there's your slope. We're saying that there's a place C between A and B that the derivative will have the same value as the slope going through those lines. That's what it says. Really kind of cool, I think. And one way to visualize this. So if here's our A and here's f of A, and here's B and here's f of B. So we have there, and that's something up here, and maybe some kind of a curve that goes like that. There's some value C, so if we drew a line through these, there's some value C where the derivative is going to have the same value. So the slope from the derivative is the same, well, the derivative is the slope, will be the same as the slope between them. That's what it says. Okay. Another version of the mean value theorem is f of b equals f of a plus b minus a times f prime of c. This should look a lot like the point slope form. Y here is your y1, b minus x1, there's your slope m. So I'm referencing that here. Okay, moving on to example 3. Determine whether or not the mean value theorem can be applied to f of x equals x to the 2/3, excuse me, f shouldn't be there, on the closed interval from 0 to 1. If the mean value theorem can be applied, find all the values of c in the open interval 0, 1 such that f prime of c equals f of b minus f of a over b minus a. So f of x equals x to the 2/3 is continuous on the interval from 0 to 1 and differentiable on the interval from 0 to 1, like that, the open interval. So the mean value theorem applies. So f of 1 minus f of 0 over 1 minus 0, that's 1 minus 0 over 1 minus 0, which is 1. So we're going to find the value where the derivative is going to be 1. F prime of x is going to be 2/3 x to the negative 1/3. So where's 2/3 x to the negative 1/3 going to be equal to 1? That's where x to the negative 1/3 equals 3/2. And what we're seeing here, this is 1 over x to the 1/3 equals 3/2. Or x to the 1/3 equals 2 over 3. We want to solve for x, so if we take x to the 1/3 equals 2/3 and make both sides, raise them to the power of 3 to undo this 1/3, what we have is x equals 2 cubed is 8 over 3 cubed is 27. So 0 is less than 8/27, which is less than 1, so C equals 8/27. That's it. That was kind of fun. So we know that between 0 and 1, at 8/27, the derivative will have the same slope as the line going through 0 and 1. Okay, going on to the last page then. Example 4. It says use a graphing utility to graph the function. I did that here. On the interval from 1 to 9. From 1 to 9. I think I went to 10. And then, let's see, find a graph the secant line through the points on the graph. F of x equals the square root of x, the endpoints in the interval from 1 to 9. So that's what we have here. And this is find a graph any tangent lines to the graph of f that are parallel to the secant line. That's what I've done there. Okay, so I can make the graphing utility to do that, but let's do this by hand. So first of all, f of 1 is the square root of 1, which is 1. F of 9 is the square root of 9, which is 3. So we're at 1, 1, and 9, 3. So our slope is going to be 3 minus 1 over 9 minus 1. That's 2 over 8, or 1/4. Okay. So we have y minus 1 equals 1/4 times x minus 9. So y minus 1 equals 1/4 x minus 9/4. If we add 1 to both sides, y equals 1/4 x minus 5/4. And that's this line right here. That's the secant line going through those 2 points. Then our derivative is 1 over 2 times the square root of x. So we take 1 over 2 times the square root of x and set it equal to the slope here. We'd have 2 root x equals 4. So the square root of x equals 2. So x would be 4. Squaring both sides. So f of 4 is the square root of 4, which is 2. So at 4 comma 2, the derivative here at 4, 2 will have the same slope as that secant line. So if we did y minus 2 equals 1/4 times x minus 4, we have y minus 2 equals 1/4 x minus 1. Adding 2 to both sides, y equals 1/4 x plus 1. That's this equation right here. And that'll do it for this section. Okay. So let me know if you have any questions about that. I hope you enjoyed this Rolle's theorem and the mean value theorem. Thank you.